So thank you very much for the invitation. So it's a great pleasure to talk about our work on deep learning applied to images graph, and I will also talk about how can we use this to solve problems in COVID-19. So actually, I have been working on deep learning for 10 plus years. So the first work I did on deep learning was 2009, and so I was a student intern at the NEC Labs. So I work with Wei Xu and Kai Yu on using deep learning for human action recognition. So this is a problem where we take videos as input and we try to predict what are the actions from these videos. And this has been used in real-world airport surveillance systems. So this was like more than 10 years ago, and more recently we have been working on more complex imaging problem. Like I'm more interested in images at the cellular and molecular level, and we also work on slightly different problems and recognition. So I think Dingao talked a lot about segmentation, etc. So this is one form of image-to-image transformation. Basically, you have an image as input, and you try to predict another image as output. And image segmentation is one of the examples. Also, we have been working on how to use deep learning on more generic structured data, like graphs. And since images that can be considered as special cases of graphs, and I will also, in each of the image and graph cases, I will also show how these techniques can be used to solve COVID-19 problems in the context of two open challenges. So as I mentioned, so the image-to-image transformation problem is you have an input image and you use some models to transform the image into another image. So image segmentation is one of the examples. You have an image as input, and you produce a segmentation map as the output. There are many other examples in medical and the biological domains that require such paradigms. So, for example, if you have a bright field image, and what we can do is we can try to predict the structures inside this bright field, and then so this is the bright field unstained bright field image, and we can use this as input to produce the structures, biological structures. And when we merge all of this together, we basically put virtual cells as output. So as another example, in microscopic imaging, so we either need to shoot a laser, beam of laser or beam of electron on the tissue, and if the laser beam is not strong enough, we usually get a noisy image like the upper part. And so what we can do is we use this noisy image as input to try to produce a clean version of the image. So this is one of the image denoising example. So basically we have a noisy image as input and corresponding clean image as output. So I think in Dingao talk, he talked about a few models to do image segmentation, and UNIT is one of the models. So in this UNIT architecture, you have a input image, and there is an encoder path and decoder path. In the encoder path, this input image is downsampled and compute some feature. Then there is a hidden representation at the bottom. Then this representation is upsampled to the original size, and there are skip connections in between. And in most of these UNIT models, people use local operators. So these local operators are, for example, convolution operation, pooling operation. So all these operations are local in the sense that the output here depends on only a local area of the input. And if you want the output to depend on larger receptor field, you have to stack many of these layers on top of each other. So So what we have been using is we use the attention operator to achieve a larger receptive field in just one step. So I think attention here is slightly different with the attention that Ding Gang talked about. So the Ding Gang talk, I think attention is more like a gate operator. You have a side pass and use a gate to basically put the attention map on the input. So the attention here is slightly different. So you have in a generic case, you have three input, Q, query, key, and value as input. You have one output. So the key here is the output will depend on. So this is a one-dimensional case where Q, are just a set of vectors. Okay. So each output vector here depends on all the input in the V. So this is some kind of a global operator. So when this is applied to higher order cases like 2D cases, so this is essentially the attention operator. So each output here will depend on every input, so that you can achieve a global feature aggregation in just one step. So this is in comparison. If you do convolution, each output here will depend only on local area. So at the superficial level, this seems to be very similar to the fully connected layers, but actually it's very different in the sense that you do not learn a weight. So these weights to combine the inputs are not learned automatically. It is based on the similarity between different inputs. And so the weight here is learned implicitly by learning different representations, because the weights here are computed based on the learned representation. So we can apply the potential operator to high order inputs. For example, if you have if your input is high order data like images or even volumetric images in high order space. So if you have an input tensor, for example, you have a four-way tensor here. What you do is usually you can apply different convolutions to obtain query key and values. So you can apply separate convolution operation to obtain key, query key and values, and then you unfold this high order tensor into three matrices. Then you give this to the attention operator. So this the operation in the red box is here is simply a attention operator. And once you compute the output of attention, it's basically a matrix. Then you fold back to a tensor, and usually this tensor is combined with every input tensor. So there is a skip connection here. So the output is the output of the non-local operator and the input. And we can also expand this to, so this is how you do this global operator when the input and output are of the same size. You have, but in the unit architecture, we know that we need the operator that perform upsampling and downsampling in the decoder, the encoder. So in the upsampling case, what we can do is, so the key observation here is the size of the output will depend on the size of the query. Okay, so if you have n queries, you have n output. So if you want to produce a larger output, you have to produce a larger query. So what you can do here is you apply transpose convolution with a stride, for example, 2. So this will produce output that is 2 times the size of the input, so that you can obtain an output that is size 2 times the size of the input. And similarly, you can do downsampling by performing a convolution of the query, so that the size of query is reduced by a factor of 2, and then the size of the output is also reduced by a factor of 2 compared to the input. So by putting all these global operators together, we still use a unit architecture. So again, we have a encoder path, and we have a decoder path, and we have a skip connection. So the only difference here is the downsampling and the upsampling operators can be replaced by while our global operators. So these are the zoom-ins of each of the global operators you can use. There are for in each of the upsampling and downsampling case, there are two different versions that we have developed. So this work is currently under revision with the Nature Machine Intelligence. This is a new journal in the Nature series. So we evaluated our method of a few biological image applications. One of them is this label-free prediction case where you have a bright field, unstained image as input, and the output is the different structures inside this biological image. So the evaluation here is based on the Pearson correlation between the predicted image and the ground truth. So this represents the Pearson correlations of our method. This is the baseline reported in this Nature method paper. And we performed this on 20 different test samples. And this is the difference, this is the significance. So you can see our method improves upon the, so this is basically a UNet architecture, so that you can see our method improves upon the UNet architecture very consistently. So this is just one example. So you have this unstained image as input, and if you use UNet, this is the output, and this is our output, and this is the ground truth. So you can see our output is more similar to the ground truth. We also applied our method on this content-aware image restoration task, which they call CARE. So this is also published in a recent Nature method paper. And so on these two data sets, you can see we use two different evaluation metrics, the structure similarity and the peak noise to signal ratio. So the larger values mean better performance here. So in each of the data sets, there are three different versions of the input with different noise levels. And so you can see this is the baseline, pretty much a UNet method. This is our method. And you can see in both cases, our method improves upon the baseline UNet. And this is a example image. So you can, one key thing of our method is the receptor field in training and test could be different because in our method, so the size of the receptor field can change during test. If you are given a larger image, so the prediction of each output can depend on larger context. So this is where the example where we increase the patch size. So this is the horizontal axis represents the size of a patch that we use, and the vertical axis is the performance of the test. So you can see if you increase the size, of the input, and if you use larger context during prediction, the performance can usually be improved. And after a certain point, the improvement will saturate. But if you use UNet, so the dashed line represents the UNet in different conditions. But because the receptor field size cannot change during prediction, so the UNet will remain the same performance. We also applied to another CARE data set, which is this 3D image projection. So the input here is a noisy 3D image. And what you try to do is you try to compute a projection of the 3D image onto a 2D plane, but at the same time you do denoising. So there are two models here. One is to project the image from 3D to 2D. After that, there is a deep learning model for denoising. And again, this is the performance here. So you can see our method improved upon baseline method quite significantly in this case. And this is an example of comparison between our method here, which is the third row here, compare with the UNet, which is the second row. And this is the last one is the ground truth on this projection example. So instead of showing all the images, I should here show you because all these images are three-dimensional images. So what here I show you is one data set, one test data set, where I show the different slices of this image as video. So this is first one is input noisy image. So the second image here shows our predictions, and the last one is the ground truth. You can see even from this very noisy image, our prediction here is very similar to ground truth in this case. So so far what I have talked about is you have an image-to-image transformation problem. You have image as input, so the image could be a noisy image, so the output could be a clean image in the case of image-to-image transformation. So one key limitation of this paradigm is in training, obviously you will need matched pairs of input and output images. So this could be very difficult for certain circumstances. So it may not be very easy to obtain matched pairs to train the model. So the other direction that we have been working on is to do self-supervised denoising. Self-supervised basically means you don't need to have the matched pairs. You only need to, in the case of image denoise, you only need to have the noisy images. So the self-supervised here means you can use, for example, you can, if you are working on imaging problem, you try to predict one part of the image from other parts of the image, so that you try to capture the correlations. So we have been very recently, we have been working on using this unsupervised method for image denoising. And for the sake of time, I won't talk about all the technical details. So the paper will be submitted to NIPS or NIPS early next month. So the result here, so I just present you the result. So these are the different data sets we have been using. And this is the first part is the traditional method. The second part is the supervised method, where you have a noise to true. This one means basically you have the matched pairs in the supervised paradigm we just talked about. There is also a noise to noise model, and this is the self-supervised method. So this is our method. And you can see using our self-supervised method, we can achieve the result. In the case of natural images, the result is very similar to the supervised case. And in the case of biological images, our results better than other self-supervised methods, but still a little bit lower than the supervised case. I think this is mainly because in the self-supervised case, we have to assume that the noise for each individual pixels are independent, and you cannot have a structural noise. So if the noise on different parts of image are correlated, our method will, because it's a self-supervised, they correlate different parts of image, then we will also try to learn the correlations among the noise. So that is probably why the self-supervised paradigm do not work so well on the biological images. So, so this is an example of the natural image case. So the first row here, first column represents the noisy input. So the last column here is the ground truth. And these are the results of different methods. So this is our method. You can see our method at the visual levels perform other competing methods slightly. So this is an example of the biological image case. And you can see here in the biological case, so this is the ground truth, and this is the supervised method. You can see the supervised method perform very well, but all these unsupervised, self-supervised methods does not perform very well, just because I think the noise patterns in the or the input are somehow correlated. So another interesting phenomenon I want to talk about is a case of transfer learning, because in the case of COVID-19, currently all of these COVID-19 data sets are very small, so it's very important to perform either self-supervised or transfer learning. So here, a very simple case is you have data set A, so you simply train a model on data set A here. So you somehow obtain one deep model, and then you do you either with or without fine-tune your model. So you perform inference on new data set, so that the knowledge from data set A can be transferred to a new data set with or without fine-tuning. So what we have been doing here is, for example, we take these three different biological data sets. Okay, so the horizontal and vertical axis represent this training and test of the three biological data sets, and so here we don't do any fine tuning. So basically that means we train the model on one data set and then perform prediction on another data set. Naturally, you can see the performance of the diagonal is usually higher, just because the training and test happen on the same data set. So for the off diagonal ones, these are real transfer learning. So for example, in this case, our training is on this data set, and our prediction is on another different data set. Okay, so but the key point here is you can see for these two different methods, the unit and our attention-based method. Okay, in almost all cases, attention-based method performs better. You can see in this all these figures. So this orange bar is higher than the blue ones. So this is one of our key observations. So the attention-based model seems to be more transferable across different data sets. So just to test our hypothesis, we applied our attention-based model on this COVID-19 imaging data set. The task here is to predict COVID-19 based on CT scans. And the data set we have been working on is from this open challenge. So the data has about 350 positive CT scans and almost 400 negative CT scans. So here is two examples of the scans, and our data here is split. I think data has been split by the organizer. So you have a training set here, so you have a validation, and there is a test set. So you compute your performance of the test set, 200 test data using F1 score, AUC, and accuracy. And so one key finding we have observed is we train our model, for example, from different CD data or even on natural images, and transfer and fine-tune the model on the challenge data. So our consistent observation is if you use attention, the model it seems to be more transferable. So currently our method ranks number 3 of the challenge. So that is my image part. In the next part, I will talk about how to apply deep models or graphs. So as we know that once you have images, this is what we can see as an image. But even for computers, it's basically a grid structure like this. So each pixel here represents a node in this graph, and computer will always see a regular lattice graph like this. And similarly for natural language. So we have a sequence of text as input, and this sequence of text can be considered as this one-dimensional graph. So one of the problems that we have been working on in the past few years is how can we apply deep models on generic graphs? So this graph part is mainly based on the work of my student Hongyang Gao, and so he also prepared most of the slides, and he will join Iowa State University as an assistant professor in August. So, so as we know that graph data has been quite common in many domains. For example, in data mining, in social networks, in And in biomedical domain, there are biomedical networks. And in the chemical domain, each chemical compound can be considered as a graph. And so we will talk about this in later part of this talk, where I will demonstrate how can we use a deep learning method to chemical data to help the detection of antibiotics. So there are a few machine learning problems in the graph domain. So one problem is called node classification. Basically, you have a graph here, and you try to predict a label for each of the nodes. And another one is called graph classification. Here, you don't associate a label with a node in the graph, but you associate a label with the entire graph. Also, you can do link prediction and community detections. So, I will talk about here is how can we I will not talk about a particular application, but I will talk about in all of these cases, what are the key operations and how can we extend deep models or images and NLP on graphs. So for example, in the citation network here, so each node here represents a document or paper, and the link here represents the citations, the references from one publication to another. And we can, for example, classify each node here as, for example, computer science, math, or chemistry. Or we can do graph classification here. The problem is we have input graph, and we try to predict the label for the entire graph. So for example, the graph can be a drug molecule, and we try to predict the property of this molecule in order to determine what could be the purpose of this drug. Either it's toxic or not toxic. So we will come back to this later. So if we look at the convolution in NLP and or in images, so you have, for example, in the case of one-dimensional, so this is the top row is your input, and when you perform convolution, so you move kernel or the input in an overlapping fashion, and they produce a set of output. So here, the key operation requires that you have for each node, there is a fixed number of neighbors, and there are orders in the neighbors. So this is one of the key challenges that when you apply these operations on graphs. So for example, in images, we have each node in image has a fixed number of neighbors, and there is an order in the neighbor. So those, in the case of images, the nodes are not permutation invariant. Okay, so I will show you why that's the case. So first, when we try to let's try to compare images with the graphs. On the left, there is an image case, and on the right, there is a graph case. So on the image, each node here, if you do not consider the boundary node, okay, so each node here has a fixed number of neighbors. But in graphs, each node might have a different number of neighbors. So this is when you apply a convolution here on the image, so the number size of your filter is fixed. But here, since you don't have a fixed number of neighbors, the size of your neighbor cannot be fixed. Also, there is no order information. In the image case, for example, if I consider this node, there is an order among the neighbors, okay? So the order cannot be changed. If you permute an order of neighbors, the image will look different. But in the graph case, the order does not matter. So if you switch order over 3 or 4, then the graph remains the same. So that is to say that there is a permutation invariant property in graphs. For example, in the case of images, if you permute the parts of this image, so these two will be different for us. But if, for example, if you switch the order of nodes here, so but the graph you keep the links, okay, so the graph remains the same. These two graphs will remain the same. So these are the challenges of how to apply deep learning on graphs. So in our work, we try to tackle this problem using two general paradigms. So Our work is based on attributed graphs, where you have a graph, and there is graph topology represented by the adjacency matrix here. So this represents how the nodes are connected. We also assume there are attributes vectors associated with each of the nodes. Here, for example, this is a two-dimensional attribute, and if we put all these attributes into a matrix X here, we obtain a feature matrix. Each row here corresponds to one node in the graph. And the two paradigms we have been working on is called feature learning and structure learning. So feature learning is you take adjacency matrix and the feature matrix as input, and you produce another feature matrix X prime as output. And in this operation, the graph topology will not change. So this is only to given graph to compute new attributes for each of the nodes. The topology will remain the same. And in the structure learning part, you have a adjacency matrix as input, you have the feature matrix as input. The output will be a new adjacency matrix and a new attribute matrix. So in this case, the graph topology will also change. So here is an example. You have an input like this, you produce an output with different feature vectors and different, even different topology. So I will talk about each of these cases separately. So feature learning graph. So you have an adjacency matrix A as input, and you have X as input. You produce X prime as output. So we all know that the GC and graph convolutional network is to perform this task, where you have a graph as input. So there basically the GCN can be decomposed into two steps. The first is called aggregation. Basically, for this node, number one, it aggregates information from different neighbors and produce a single representation here. And then you do a transformation in the second step. So this can be achieved mainly in two different operations. First is, as we mentioned, the GCN, the graph convolutional network. The other one is the graph attention networks. So we will talk about each of these in detail. So here you have a graph as input, and each node is associated with an attribute. So in the aggregation step in the GCN, basically what you do here is you simply do a weighted summation of the features of all the neighbors. Okay. So for example, here the feature for this node will be simply the feature weighted summation feature from these three different neighbors. And of course, you can do self loop. In that case, this will also include the feature from yourself. So if you use this formula here, okay, so there is a degree d to the power minus 1. So this essentially controls the weight. If you use this kind of weighting, basically each of the neighbors has a fixed and the same weight, 1/3 in this case, because node number 1 has 3 neighbors. And once you compute this, you have feature vector for this node, then you do a transformation. This transformation is simply you apply a W, okay? W is the matrix here. And if you view this graph as images, so this transformation W is basically a 1-by-1 convolution. So the key limitation of GCN here is you can see. So in convolutional images, we learn a filter. When we learn a filter, the filter weights are learned automatically during training. And in GCN, you don't learn any weight. So these weights are hardwired. Okay. So you don't learn any weight. You basically do a weighted summation of your neighbor's feature using fixed weight. Then you do a transformation. So the only learnable part here lies in the 1-by-1 convolution W. So what we have been trying to do is we try to enable the learning of these weights. So what we can do in this KDD 2018 paper, we try to do top K selection. So for this node, we simply put all these feature vectors in a matrix, and we do top K selection. We select the top K largest features. In this case, so 4 and 6 survive in the first feature, and 8 and 4 survive in the second case. So we select fixed number of features, then we do one-dimensional convolution on this selected feature. Then we do transformation. So this will enable the learning of the weights in the context of graph. Also, we have been working on another paradigm called the graph attention. In the graph convolution case, the weights here are learned explicitly. You have a weight for each node. And in the graph attention case, the weights are learned implicit because the weights are determined based on the relationship between inputs, and the input features are learned. So by learning the feature input, you learn the weights implicitly. So here is an example. So for example, if you try to learn the feature for node number 1, okay? So you first compute the similarity between node number 1 and each of the neighbors. Here, the node 4, 3, and 2. So then you compute the similarity. Then the node feature for node number 1 is a weighted summation of the neighbor features using the similarity score S here. So this is the paradigm here. So you can see here. So this S are not learned automatically, but these features are learned automatically. By enable the learning of these features, you learn basically you learn the similarity. So that is why in the graph attention, these weights are learned implicitly by learning the features. So in the graph attention network, so currently this is called the soft attention. Basically, for each node here, the feature will depend on all the neighbors. So this is not a very desirable property. So in all the image case, we know that this is called the soft attention. And we know that usually hard attention achieves a better performance and better interpretability because each node may only attend a subset of the neighbors. So in this recent work, we try to achieve hard graph attention. So what we do here, just in general, is we compute a score for each of the nodes. So this score is computed by projecting a feature or a P. P is basically here a vector. And P is computed, P is trained throughout the training by projecting X to a one-dimensional space. We obtain a score for each of the nodes. And then we use your score to rank all of your nodes, and we select a subset of your nodes to attain. So here is the example. So this is the input. Suppose we set K equal to 2. And what we can do is we use the projection to project all these nodes into one-dimensional score. And for example, if we use a score, probably this one will have a lower score, for example, and this one will be skipped. So the attention here on 1 will be only computed based on neighbor from 3 and 4. So this one, number 2, is ignored in this paradigm. So, and similarly, we also do, of course, we do a transformation. So this is a result of node classification. So we have a few data sets, public domain data sets, and these are the statistics of the data sets, and these are the prior method or node classification, and this is the result of our method. So this data set has been used extensively recent years, and the performance here, you can see, tend to saturate, but still we can improve upon our prior methods. Also, this is the result of graph classification. So basically, you have a label for the entire graph. And this is a result of all the prior methods, and this is a result of the graph hard attention. You can see by using hard attention, you can not only improve the prediction accuracy, but you can also improve the interpretability because each node only attends to a subset of the neighbors. So in the next part, I will briefly talk about structural learning. So as I mentioned, in structural learning, so we not only learn the feature, but we also learn new topology. So the reason why we need this is because, for example, in the image case, so we have a pulling and unpulling in the unit, try to change the size of the image. That basically corresponds to structural learning in graph. So you have an input graph, you produce a smaller output graph. or the other cases, you have a smaller input graph, you try to produce a larger output graph. So these are the two examples of structured learning. We can do pooling or unpooling. So in the pooling case, you have a graph as input, you produce a graph with a smaller number of nodes as output. So unpooling is the reverse case, where you have a smaller graph as input, you produce a larger graph as output. So this basically corresponds to the pooling and unpooling in our images. For example, in the unit case, in the encoder, you do pooling, and in the decoder, you do unpooling. So what we have been doing is we designed a set of operations for pooling and unpooling our graphs, and we eventually come up with this graph unit paradigm. So in graph pooling case, what we do is, again, we are doing this based on node ranking score. For example, this is the input graph. We compute a projection of each of the feature vectors so that we come up with a node score for each of the nodes in the graph. Then we select the top k node. Here, in this case, if we select k equal to number 3, you can see this node will be ignored in the selection process, and we obtained a smaller graph. So this is the mathematical formula. So we basically do a projection to compute score, then we do a ranking and do node selection based on the ranking scores. So this work was published in ICML last year. So this is the process. You have an input graph, you compute your projection. Basically, you can compute all the feature vectors onto a P, and P is the length. So the direction here is a length from the data. Then you come up with a ranking score for each of the nodes. And then you select the top k nodes. For example, here are the top 3 nodes, and we skip this node, and we obtain a new graph. And one problem with this method is it may produce isolated graphs. For example, once we are here, if we do a ranking, we might try to skip this node in the next step, and then these 2 nodes here will be isolated. So we try to address that problem using something called topology-aware pooling layer, because in the first method, when you compute your projection here, okay, so the projection is completely based on the feature vectors, not the topology at all. So in this topology-aware pooling layer, we compute ranking score again for each node, but node ranking or the ranking score for each node is computed based on the topology, essentially with the neighbors. Here is an example. So what we do here is we have input graph, and we first compute the attention score, basically the similarity score between each pair of connecting nodes. So these numbers represent the attention score between pairs of nodes. Then for each node, the score of each node here is the average of the scores of all the neighbors. For example, so the ranking score for this node is the average of these 2 numbers. And similarly, the ranking score for this node is the average of these 2 numbers. Once you compute the ranking score, you again do node selection based on your ranking scores. So this is our recent work on topology-aware pooling. And also we do unpooling. So if you have a smaller graph, how can you produce a larger graph in the decoder? So we simply use the idea of unpooling in our images. So there is unpooling operation on image where you memorize the location in the encoder path. In the downsampling path, you memorize the location of the maximum value, and in the decoder phase, you restore the location. So we do something similar. So we memorize the topology of the graph and pass the information from the encoder. So this is the encoder to the decoder. And in the decoding phase, we restore the structural graph, but the feature vector is not restored. So we simply use a dummy feature vector, but after one step, this feature will be filled. If you connect a convolution here, so the feature vector here will be computed based on neighbors. So by putting all of this together, we basically come up with this graph unit. So you have an input graph, and you do convolution, you can do pooling, and you obtain a hidden representation here, and then you can do unpooling to restore the original structure, and you can do skip connections. And this is the result of node classification. So this is a dataset statistics, and these are the prior methods. This is the result of if you use a graph pooling layer inside the graph classification. This is node classification. Also, you can do graph classification. Okay, so these are the results of our method using graph pooling and topology aware pooling across many different data sets. You can see our method can improve upon this prior method. So in the last two slides, I will talk about how can we use graph methods to solve problems in COVID-19. So we also participated in this challenge organized by Tommy Jacola and MIT. So what they try to do is they observe that a high proportion of the non-surviving patients with COVID-19 developed a secondary infection. So infection by a particular bacteria, pneumonia. And this particular bacteria can be caused by a wide array of bacteria species. So this open challenge is trying to identify a new antibiotic for this bacteria using machine learning. So what they have been doing is basically they have a molecule as input. So the molecule here is represented a graph. So each of the nodes here represents an atom, and the connectivity here represents the bond between atoms. And there are also feature vectors for each of the atoms by the compute, for example, based on the property of the atom. There is a feature vector associated with each of the compounds here. And what they try to do is they try to predict different properties of this molecule. So one potential, for example, what they have been doing is using graph convolution. This will enable the extraction of some features here and then predict label for this attributed graph. So this is the current leaderboard. So we have been working on this only very recently. So I have a couple of students working on this probably in the past 1 week. And currently our result is number one on this leaderboard. So I think the comparison here is based on AUC, other ROC, and our PRC, precision recall curve. Okay, so the second place on the leaderboard is from Yuri's group from Stanford, and they use extra data. They use pre-trained graph model. Basically, they have a set of molecules from different data sets. They use a self-supervised method to pre-train the network and then fine-tune on this data set. We didn't use any of the extra data set. We only used about 2,000 training data given by the challenge. Okay, so that's pretty much about my talk. So just a quick recap. I talk about image transformation problems using global operators. Basically, you have an input image, you try to transform it into an output image, and we can use the global operators to achieve a larger context in just one step. And this also a key take message here is it's very different with a fully connected layer. You had the received field in training and in prediction can be different. And we also observe that our model is more transferable. If you use attention in your model, the model is more transferable across data sets, even from natural image to medical images. And we designed different deep learning operators for graphs to perform structure and feature learning. And we demonstrate how can we use this to solve problems in COVID-19. And our application on COVID-19 is simply based on open challenges. So I think Dinggang did a lot of real-world examples how to solve this in real world. But since we are not in the in that domain, we don't have first-hand data. So the best we can do is we work on these open challenges. But I think we hope we can work with other domain experts like Dinggang to really apply our method to solve problems in the field. So this is my team who did all the work, and I think the graph part of work on COVID-19 is led by Lee, and he has defended recently, and he will join Microsoft. And thank you.